Hello everyone, we are from Group 7 want to present about elementary functions part 1. The members of Group 7 are Gilang Kusumalestari and Imanina Fitri Rahmawati. We want to explain about exponential function, logarithmic function, branches and derivative of logarithms, some identities involving logarithms, complex exponents, and the last trigonometric function. For the first, the exponential function. For complex number c equal to x plus iy, exponential function is defined by exponential of c equal to exponential of x plus iy equal to exponential of x times exponential of y, where Euler's formula exponential of iy equal to cos y plus I sin y. Then fc is equal to exponential of c equals exponential of x times exponential of iy equal to exponential of x cos y plus I sin y. The exponential function is entire function because the arranger functions and derivative is continuous anywhere and satisfy Cauchy-Riemann equations. So we get the differential is exponential of c. If c equal to x plus iy and w equal to u plus iv, then exponential of c plus w equal to exponential of c times exponential of w. The characteristic of exponential function. For the first, exponential z not equal to 0. Second, exponential of c plus 2pi equal to exponential of c for periodic function with 2p period. Third, exponential of c over exponential of w equal to exponential of c minus w. And for the last, the absolute value of exponential z equal to exponential x, and argument of exponential z equal to y plus 2np. For n equal to 0, plus minus 1, plus minus 2, and so on. For examples, determine all z so that exponential z equal to 1 plus I. Solution. In order to find numbers c equal to x plus iy such that exponential of c equal to 1 plus I, we write as exponential of x exponential iy equal to square root of 2 exponential ip over 4. Regarding the equality of two non-zero complex numbers in exponential form, exponential x equal to square root of 2 and y equal to p over 4 plus 2np for n equal to 0 plus minus 1 and so on. Because ln exponential x equal to x, it follows that x equal to ln square root of 2 equal to a half ln 2 and y equal to 2n plus 1 over 4 p. For n equal to 0 plus minus 1 and so on. So c equal to a half ln 2 plus 2n plus 1 over 4 p I for n equal to 0 plus minus 1 and so on. For the second examples, determine all c so that exponential z equal to negative 1. Solution. Equations can be written as exponential x exponential iy equal to 1 exponential ip. Equation of two non-zero complex number in exponential number. Exponential x equal to 1 and y equal to p plus 2np for n equal to 0 plus minus 1 and so on. So x equal to 0, and we get z equal to 2n plus 1 pi for n equal to 0 plus minus 1 and so on. And we go to the next slide, the logarithmic function. The definition of logarithmic function is based on solving the equation exponential of w equal to z for w, where z is any non-zero complex number. When z and w are written, z equal to r exponential of I theta for theta more than minus v and less than equal p, and w is equal to u plus iv. Equation exponential w equal to z becomes exponential u exponential iv equal to r exponential I theta. The equality of two complex numbers expressed in exponential form, exponential u equal to r and v equal to theta plus 2np, where n is any integer. Since exponential u equal to r is 2 equal to ln r, so w equal to ln r plus I theta plus 2np. Thus, if we write log c equal to ln r plus I theta plus 2np, equation exponential w equal to c tell us that exponential log c equal to c non-zero, which serves to motivate expression log c equal to ln r plus I theta plus 2np for n equal to 0 plus minus 1 and so on. As the definition of the multiple valued logarithmic function of a non-zero complex variable c equal to r exponential I theta. For example, if c equal to minus 1 minus square root of 3i, then r equal to 2 and theta equal to minus 2p over 3. Hence, log negative 1 negative square root of 3i equal to ln 2 plus I minus 2p over 3 plus 2np equal to ln 2 plus 2 n minus 1 over 3 pi for n 0 plus minus 1 and so on. Log c equal to ln r plus I theta 2np, so that log c equal to ln absolute value of c plus I argument c. Absolute value of exponential z equal to exponential x, and argument exponential z equal to y plus 2np for n equal to 0 plus minus 1 and so on. When z equal to x plus iy, we know that log exponential z equal to ln absolute value of exponential z plus I argument exponential z equal to ln exponential x plus I y plus 2np equal to x plus iy plus 2npi equal to z plus 2npi for n equal to 0 plus minus 1 and so on. When n equal to 0, log c equal to ln r plus I theta. Log c is well defined and single valued when c not equal to 0. Log c equal to log c plus 2npi. It reduces to the usual logarithm in calculus when c is a positive real number, c equal to r. C equal to r exponential I theta. Log c equal to ln r plus I theta becomes log c plus ln r. For the second example, from log C equal to ln R plus I theta plus 2 and P, we find that log 1 equal to ln 1 plus I 0 plus 2 and P equal to 2 and Pi when n equal to 0 plus minus 1 and so on. As anticipated, log 1 is equal to 0. So although it is unable to find logarithms of negative real numbers in calculus, we can now do so. For the last examples of logarithmic function is observe that log negative 1 equal to ln 1 plus I P plus 2 and P equal to 2n plus 1 Pi for n equal to 0 plus minus 1 and so on, and that log minus 1 equal to Pi. Go to the next slide, branches and derivatives of logarithms. If z equal to r exponential I theta is a non-zero complex number, the argument theta has any one of the values theta plus 2 and p for n equal to 0 plus minus 1 and so on, where theta is argument c. Hence the definition log c equal to ln r plus I theta plus 2 and p for n equal to 0 plus minus 1 and so on. Of the multiple valued logarithmic function can be written log c equal to ln r plus I theta. A branch of a multiple valued function f is any single valued function f that is analytic in some domain at each point of C of which the value fz is one of the values of f. The requirement of analyticity of course prevents f from taking on a random selection of the values of f. The function log c equal to ln r plus I theta is called the principal branch. For examples, when the principal branch log c equal to ln r plus I theta is used, one can see that log I power 3 equal to log minus I equal to ln L minus I p over 2 equal to minus p over 2i, and 3 log I equal to 3 ln L plus I p over 2 equal to 3p over 2i. Hence, log I power 3 not equal to 3 log I. And then, some identities involving logarithms. If z1 and z2 denote any two non-zero complex numbers, it is straightforward to show that log c1 c2 equal to log c1 plus log c2. This statement involving a multiple valued function is to be interpreted in same way that the statement argument c1 c2 equal to argument c1 plus argument c2. Since absolute value of c1 equal to absolute value of c1 times absolute value of c1, and since these moduli are all positive real numbers, we know from experience with logarithms of such numbers in calculus that ln absolute value of c1 c2 equal to ln absolute value c1 plus ln absolute value c2. So it follows from the equation above that ln absolute value c1 c2 plus I argument c1 c2 equal to ln absolute value c1 plus I argument c1 plus ln absolute value c2 plus I argument c2. For examples, to illustrate statement 1, write c1 equal c2 equal minus 1 and recall from example 2 and 3 in section 30 that log 1 equal to 2n pi and log minus 1 equal to 2n plus 1 pi, where n equal to 0 plus minus 1 and so on. Noting that z1 z2 equal to 1 and using the value log c1 z2 equal to 0 and log c1 equal to pi, We find that equation 1 is satisfied when the value log C2 equal to minus pi is chosen. If on the other hand, the principal values log 1 equal to 0 and log minus 1 equal to pi are used, log C1 C2 equal to 0 and log C1 plus C2 equal to 2pi for the same numbers C1 and C2. The statement 1, which is sometimes true when log is replaced by log, is not always true when principal values are used in all three of its terms. Verification of the statement log C1 over C2 equal to log C1 minus log C2, which is to be interpreted in the same way as statement 1 is left to the exercise. We include here two other properties of log C that will be of special interest. If C is a non-zero complex number, then C power n equal to exponential n log C, for n equal to 0, plus minus 1, and so on. For any value of log C that is taken, when n equal to 1, this reduces of course to relation 3. Equation 5 is readily verified by writing C equal to r exponential I theta and noting that each side becomes r power n exponential I n theta. It is also true that when C not equal 0, C power 1 over n equal to exponential 1 over n log C, for n equal to 1, 2, and so on. That is, the term of the right here has n distinct values, and those values are the nth root of C. To prove this, we write C equal to r exponential I theta, where theta is the principal value of argument C. Then, in view of definition 2, section 30 of log C, exponential 1 over n log C equal to exponential 1 over n ln r plus I theta plus 2kp over n, where k equal to 0, plus minus 1, and so on. Thus, exponential 1 over n log C equal to n root of r exponential I theta over n plus 2kp over n, for k equal to 0, plus minus 1, and so on, because exponential I2 kp over n has distinct values only when k equal to 0, 1, and so on until n minus 1. The right hand side of equation 7 has only n values. That right hand side is in fact an expression for the nth root of C, and so it can be written C power 1 over n. This established properties 6, which is actually valid when n is a negative integer too.
Okay, the next material is complex exponent. In the previous material, we have known that complex function z equals to r exponential I theta can be written as z equals to exponential log z by the definition of the multiple value log function of a non-zero complex variable. We can use this definition in complex exponent function. When z is not equal to 0 and the exponent c is any complex number, the equation z power c equals to exponential log z power c. By using the properties of a logarithmic function, that is, log a power n is equal to n times log a, we can write the equation into z power c equals to exponential c log z. The equation z power c is defined by means of the equation where log z denotes the multiple valued logarithmic function. As the properties of log z in the previous material, if z is a non-zero complex number, the equation z power n is equals to exponential n times log z, where n is equals to 0, plus minus 1, plus minus 2, etc. for any value of c that is taken. And the equation c power 1 over n is equals to exponential 1 over n times log z, where n is equals to plus minus 1, plus minus 2, etc. This definition shows that the equation z power c is equals to exponential c times log z when z is not equals to 0 and the exponent c is any complex number is valid when c equals to n, where n is equals to 0, plus minus 1, plus minus 2, etc. And c is equals to 1 over n with n is equals to plus minus 1, plus minus 2, etc. Now we move to an example. Power of c are, in general, multiple values as illustrated by writing I power minus 2i is equals to exponential minus 2i log I. We have known that z is equals to exponential log z, and log z is equals to ln r plus I times theta plus 2np. From the equation, we know that z is equals to I, or in the other form, z x, y is equals to 0, 1. Obviously, we can find the value of radius r and theta by the formula that we have learned in the previous material. We know that r can be found by the formula r equals to square root of x squared plus y squared. Since the value of x is 0 and the value of y is 1, we find that the radius r is 1. It is also known that tan theta is equals to y over x. So, tan theta is equals to infinity and theta is a half p. Now, based on the equation log z is equals to ln r plus I times theta plus 2np, the equation log I power minus 2i is equals to log 1 plus I times a half p plus 2np. Since log 1 is equals to 0, the equation is changed into log I power minus 2i is equals to I times p plus 4np, or I times p times 1 plus 4n. Then, exponential log I power minus 2i is equals to exponential I times p times 1 plus 4n. In the logarithmic function material, exponential log z is equals to z. So, exponential log I power minus 2i is equals to I power minus 2i. The equation is changed into I power minus 2i is equals to exponential I times p times 1 plus 4n. Thus, I power minus 2i is equals to exponential p times 1 plus 4n, with n is equals to 0, plus minus 1, plus minus 2, etc. We have known that if z is equals to r exponential I theta and alpha is any real number, the branch of the logarithmic function is the equation log z equals to ln r plus I theta, where r is positive and theta is on the interval from alpha until alpha plus 2p. This equation is single-valued and analytic in the indicated domain. Then, in the complex exponent function, the branch of the function z power c is equals to exponential c times log z is also single-valued and analytic in the same domain. The derivative of such a branch of z power c is found by first using the chain rule. The derivative of z power c is equals to the derivative of exponential c times log z, since the equation z power c is equals to exponential c times log z. We have known that the derivative of exponential alpha log beta is equals to alpha over beta times exponential alpha log beta. So, the derivative of exponential c log z is equals to c over z times exponential c log z. Since z is equals to exponential log z, the equation is changed into c times exponential c log z over e log z. The solution will be c times exponential c minus 1 log z. Then, the derivative of z power c is equals to c times z power c minus 1, where the absolute value of z is positive and theta or argument z is on the interval between alpha and alpha plus 2p. Then, the principal value of function z power c is z power c is equals to exponential c log z, and the principal branch of the function occurs on domain the absolute value of z is positive and the argument z is between minus p and p. Move to an example. The principal branch of z power 2/3 can be written as r power 2/3 times cosine 2/3 I theta plus I sine 2/3 I theta. Why? Because log z power 2/3 is equals to 2/3 ln r plus 2/3 I theta. Then, exponential log z power 2/3 is equals to exponential 2/3 ln r plus 2/3 I theta. By using the properties of exponential function, the equation exponential 2/3 ln r plus 2/3 I theta can be written as exponential ln r power 2/3 plus 2/3 I theta. And by using the properties of exponential function again, the equation can be written as exponential ln r power 2/3 times exponential 2/3 I theta. Since exponential log alpha is equals to alpha, so exponential ln r power 2/3 is r power 2/3. Then, the equation is changed into r power 2/3 times exponential 2/3 I theta. Since exponential iy is equals to cos y plus I sin y, then exponential 2/3 I theta is equals to cosine 2/3 I theta plus I sin 2/3 I theta. Then the solution is r power 2/3 times cosine 2/3 I theta plus I sin 2/3 I theta. The next material is trigonometric functions. In Euler's formula material, we have known that for every real number x, exponential ix is equals to cosine x plus I sin x, and exponential minus ix is equals to cosine x minus I sin x. So we have exponential ix minus exponential minus ix is equals to cosine x plus I sin x minus cosine x plus I sin x. Then, exponential ix minus exponential minus ix is equals to 2I sin x, or sin x is equals to exponential ix minus exponential minus ix over 2I. We also have exponential ix plus exponential minus ix is equals to cosine x plus I sin x plus cosine x minus I sin x. Then, exponential ix plus exponential minus ix is equals to 2 cosine x, or cosine x is equals to exponential minus ix plus exponential ix over 2. This concept of Euler's formula can be used in complex variable. The sine and cosine functions of a complex variable z is exponential iz is equals to cosine z plus I sine z, and exponential minus iz is equals to cosine z minus I sine z. By using the same way, we get sine z is equals to exponential iz minus exponential minus iz over 2i, and cosine z is equals to exponential iz plus exponential minus iz over 2. These functions are entire since they are linear combinations of the entire function exponential iz and exponential minus iz. The derivatives concept in real function is also used in these exponential functions. The derivative of exponential iz is equals to I times exponential iz, and the derivative of exponential minus iz is equals to minus I times exponential minus iz. From equation sinus z is equals to exponential iz minus exponential minus iz over 2i, and cosine z is equals to exponential iz plus exponential minus iz over 2. Then the derivative of sine z is cosine z, and the derivative of cosine z is minus sine z. The sine and cosine functions remain odd and even. So sinus minus z is equals to minus sine z, and cosine minus z is equals to cosine z. A variety of identities are also carried over from trigonometry. The first identity is sine z1 plus z2 is equals to sine z1 times cosine z2 plus cosine z1 times sine z2, and cosine z1 plus z2 is equals to cosine z1 times cosine z2 minus sine z1 times sine z2. The second identity is sine 2z is equals to 2 sine z cosine z, and cosine 2z is equals to cosine square z minus sine square z. Sine z plus a half b is equals to cosine z, and sine z minus a half b is equals to minus cosine z are also carried over to this trigonometric function of complex variable. Sine square z plus cosine square z is equals to 1 also holds. The periodic character of sine z and cosine z is also evident. The periodic characters are sine z plus 2b is equals to sine z, sine z plus b is equals to minus sine z, cosine z plus 2b is equals to cosine z, and cosine z plus b is equals to minus cosine z. The other trigonometric functions are defined in terms of the sine and cosine functions by the expected relations. The functions are tan z is equals to sine z over cosine z, cotan z is equals to cosine z over sine z, and secant z is equals to 1 over cosine z. The derivative formula also occur in these trigonometries. The derivative of tan z is equals to secant square z. The derivative of cotan z is equals to minus cosecant square z. The derivative of secant z is equals to secant z times tan z. The derivative of cosecant z is equals to minus cosecant z times cotan z. The periodicity is also defined for tan. The periodicity is tan z plus p is equals to tan z. That's all for our material. Thank you for your attention and see you.